This is a reminder for those who need to sign for EE 5027. All right, so let's start our lecture today. So this is lecture 6, and the topic that we will discuss is full Bayesian and predictive distributions for classification. So for this one, let's have a quick recap because we already learned a few things on the full Bayesian side. Okay, so full Bayesian. A quick recap here. So let's start with the input. What is the input that we have here for full Bayesian, for classification especially? What will be the input? Anyone? T bar. And when we say T bar is always with another one which is X n bar or Xn. Yeah, in this case, because classification is likely to be Xn bar. And we have Tn bar and n equals to 1 up to number of training samples. So this is the input in the training, by the way. Training stage. Right. And Tn here, Tn, oh yeah, Tn bar is of course T, let me think. So not Tn bar, it's not bar, but label 0 or 1. So T bar equals to T1, T2 until Tn. Well, basically, there is if you put it in the vector format, then that will be the T bar vector. And the output that we want to have is what in the training stage? What will be the output? W bar. Right. And if you use a full Bayesian, what expression that we have to use? What will be the expression for full Bayesian? So this one is the first step, right? So the first step, yeah. So what is the first step here? What is the first step that we always use in the of the three steps? Yeah, data modeling, or in this case, full Bayesian modeling. Full Bayesian data modeling. And when you say data modeling for full Bayesian, what do I need to write? What do you need to write in the first place, in the beginning? Anyone? What will be the first mathematical expression that we have to write down? We start with what? What letter that I have to write? No, why? Data modeling. Oh, yeah, it's why, but we don't use why that much anymore here in classification in terms of the inference techniques based on Bayesian. It's always with P. Okay, so you have to remember this. You always start with P, which is probability function. All right? So what is the probability function that we have to write here? P of what? Probability of P of W given T bar, right? Or T bar here, or W is always associated with X. And when you say Y, actually, when you say Y, it's usually P Y there, right? And Y, even P, something like this, if you want to use Y. And Y, we know Y is a function of W and X. But anyway, so the output that we want is W, so that's the more precise expression that we will use. So this one equals to what? Not integral, this is we use full Bayesian expression here. This is what is the name of this expression? What is the name of this function here? It is posterior, right? So posterior equals to what? Likelihood multiplied by likelihood is this one multiplied by the prior divided by the evidence or the P of P. Yeah. So this is something that we have to solve in full Bayesian framework. Okay, so now the problem is that we have to define further, right? Especially for the likelihood. For the likelihood, we have P of T bar, W bar, equals to what? Remember, anyone? This one we discussed for the MLE one. If you don't remember, that's fine. It's in the product of n, sigmoid n, power 2, Tn, 1 minus sigma n, power 2, 1 minus Tn. Yeah, so this is called likelihood. Likelihood function is sigmoid function of the two possible labels. So the two possible labels for Tn here is actually either 0 or 1, plus 1 or plus 2. Right, so then we also have prior. For prior, P of W bar equals to what? Prior. How do we model prior? Right. Gaussian of W bar with a mean of 0. Let's make it more general, and 0, which is of course 0. And standard deviation alpha inverse I, right? And this is 0. Any questions so far? we discussed last week actually why this PW is Gaussian and what is the meaning behind. You have to know the meaning behind, by the way. You have to be able to imagine that W or the space that you deal with is multiple dimensional space, and we set M, and M is the problem, right? M is the complexity. M is when you transform your dimensionality, your original dimensionality, into higher dimensionality. So remember that the case here for the likelihood, we have X n bar space, and we have to transform this into phi n bar. Right? That's really the basic idea. You have to keep it in mind that there is a space transformation in MLE when we use a basic function. So what is the dimensionality of Xn, for example, or what was the label or the variable that we use for Xn? Dimensionality is t, t by 1. So n phi is m by 1, that's correct, m by 1. And what is the correlation between t and n? What is the correlation between t and n?
T is bigger than N.
No, this is the opposite actually. M has to be bigger than t. Yeah, equal will not change anything because equal means that the same space, so that's not really interesting. You transform this into higher space and it's much higher now. Why is that? Why you need to separate in the higher space?
Sometimes in the lower dimension you can't see them.
Yeah, so in the lower dimension, the t dimension, what we have is like a situation like this. It is not linear. You cannot separate linearly in this dimensionality. That's why you have to transform this into higher space. If it's lower space, then you make the situation worse. And if you don't change the space, then you cannot separate them linearly. So you have to transform this into higher space so that you can have the opportunity to find a hyperplane that can separate the positive and negative in a linear way. And that's why M is very important. If M is not enough, you will not be able to separate the positive and negative in a linear way. Right? So you have to find a space high enough so that you can separate the positive and negative in a linear way. When I say linear way, you use a hyperplane to separate the two parts. This is very important concept. So if you don't understand this yeah.
Full hold, unless D contains unnecessary data or unnecessary dimension, then we can choose M lower than D to get rid of the unnecessary.
That's right. Yeah, I forgot to mention that. That's why it's okay when you have features that are not necessary, right? When you have features that are not necessary, of course, it's not always high up. Of course, in the high up, it's not really harmful, but sometimes it's not necessary. You can easily get into a opportunity bound in that case. More vulnerable than if you don't have unnecessary features. But anyway, if you know that there is an unnecessary feature and it's taking up a lot of dimensionality, of course, you can reduce into smaller dimensionality to avoid overfitting. But that one is a bit advanced, a bit special case, right? If you don't understand that, just think in this way that M is greater than D because in the original dimensionality, you can separate the positive from the negative in a linear way. Okay, any questions here? Any other questions? Again, this concept is very important. If you don't understand this, you will get lost all along the way for classification. Okay, so this is the important thing here. The likelihood here need what kind of M? Smaller or bigger M? The likelihood is a bigger M because the bigger M guarantee and much more likelihood to do the job, right? To separate the positive and negative. But that one is the problem of fitting, right? And to reduce that one, you have to kill off the dimensionality. You have to kill off some axis. some coordinates. So that's the job of the prior, to reduce the dimensionality of your space. Any questions here? Okay, so don't forget about M. In this equation, there is M that is very important. Okay, so now let's try to solve this problem. We know that the issue with this, the issue of solving this Gaussian or Bayesian inference here is, the issue here is what? If you want to solve the problem, the evidence, the P of T is very difficult to compute. It is prohibitively expensive if you do it in discrete, and analytically difficult if it is in analog, if you have to solve the integral function. And what is the solution for this integral problem? Yes, you will find a specific function for P, the likelihood and the prior. Why? Because in the end of the day, this is the main problem, right? And what we want here is that we know that P of T bar integral of P W T bar T bar, right? And this one equals to P of T given T W bar P of W, sorry, not T W and TW. That's something that we want to solve, right? That's the definition of P of T. Now, the question is that, or not the question, but the idea is that we want to have a special case when we can force this to be Gaussian, and we want to force this as a Gaussian as well. If we force these two likelihood and the priors as a Gaussians, then we can solve this integral function. This is a special case to solve the problem of the integration. It's very rare, though, right, that we can have Gaussian and Gaussian, especially in practice, in the real world. Any questions so far? Okay, so if there's no question, that's the basic idea, that we want to find whether or not it is possible for the likelihood and the prior to be Gaussian. So let's see. So the prior is already Gaussian. So this one is already Gaussian. You don't need to worry about that part. Now, the question is, how about the likelihood? Whether the likelihood is Gaussian or not. So as you can see there, we learned this last week, that the first part, so P of T here, so let me see if I can get clear. So this one, right? So that one is consists of two things. So assume that, you know, n equals to 2. Assume that n equals to 2, then you will have sigma 1 T1 1 minus sigma 1 minus T1 multiplied by sigma 2 T2 1 minus sigma 2 1 minus T2, right? Assume that we have 2 points, positive and negative. So this one, again, I assume T1 is positive or 1 and T2 is negative or 0. Okay, so in that case, if I assume in that way, what happened with sigma 1 T1? Sigma 1 T1 becomes sigma 1. 1 minus sigma 1, 1 minus T1, 0, right? So that one is 0, that become 1. So then we can move to sigma 2. Sigma 2 T2 give you, yeah, sigma 2 T2 is 0. If T2 is equal to 0, sigma 2 is not necessarily to be 0, but close to 0, but there is some number there. Some number power to 0 equals to 1. So we ignore that one. So the other one is 1 minus sigma 2. 1 minus T2 is 0, power to 1. All right, so we have that equation then. So the first one look like what? The first one look like what? Look like ants, right? As letter ants. And that one is sigma 1. And sigma 2 look like the inverse of that one. So if you multiply this, what happens? If you multiply these two, then you will end up with something look like Gaussian, but it's not Gaussian, but it's something look like Gaussian, something like that. Right? And further on, so the likelihood look like this. So this is how the likelihood look like. The likelihood look like a Gaussian. It's not Gaussian, but it looks like Gaussian. Okay, any questions here up to this point?
Is this the same? We have multiple points.
Yeah, a good question. You can try. So basically, if 2 points will give you something like this, right? 2 points give you something like this. And imagine that you have two this kind of thing. What it look like? It's almost the same, right? If you multiply 3 times, it's almost the same, but smaller and smaller and smaller for that. But it looks like the same kind of thing. Yeah.
What if most of the 90% of the THC would be leaning to one side?
Yeah, that will be leaning to a bit biased to a certain shape. It is not really like this, but it is slanted towards that kind of bias. Okay, if it is not balanced. But don't worry, even if you have that kind of thing, it is not the end of the story, because you have to multiply this with the prior. Your prior is a Gaussian. So this one multiplied by Gaussian is somehow like this, or a bit slanted sometimes, right? A bit biased sometimes to certain values. Now, the question is that if we have this kind of function, you can imagine a function that looks like Gaussian, but it's not Gaussian. The idea is to force it to be a Gaussian. The multiplication of the likelihood and the prior have to be a Gaussian. So the basic idea is that the likelihood multiplied by the prior is forced to be Gaussian. So this is the basic idea. We try to force the shape of the multiplication between likelihood and prior to be Gaussian. Is it understandable? So in other words, so I can write down here, P of W given P bar equal to PW P bar P of W bar divided by the integral of P W P W P bar and P of W bar dW bar, right? So the top one, the top side here, we force it to be Q, to be a function of Q of W, and this Q of W has to be a Gaussian, where M, I do not know, N perhaps, or Mn. We do not know Mn and Sn, but we force this into this kind of form. That's really the basic idea. We force the top side here to be a Gaussian function. Is this understandable? Sorry? Oh, is that, oh, yeah, the likelihood is wrong. Thank you. Okay. Any questions so far here? You need to understand this. This is really very basic concept that we want to force the multiplication of the likelihood and the prior to be Gaussian, and the Gaussian here represented by Q. And Q here has a name. It's a proposal function. It's called proposal function. And the proposal function is just a name. Don't worry about that. It's a proposal function, and the proposal function is has to be Gaussian. This is how we force the multiplication to be Gaussian. And of course, if this approximation is so different from the original function, the approximation will be a bad approximation. But if the approximation is very close to the original function, then it's a good approximation. So you need to be careful in practice when looking at this or using this kind of technique or a Gaussian approximation or approximation approach, right? So you need to look at this function here. You need to look at the function and whether that function really look like Gaussian or not. If it is really look like Gaussian, then you can be secure. You can be confident that it will be a good approximation. But if the function is so different from the Gaussian, then you should not use Gaussian in the first place to approximate this function. All right? Does it make sense? Any question? Okay, so now assume that you can successfully have Q representing the numerator with a Gaussian function. What happened with your denominator then? What is the value of your denominator? The whole thing is here. The whole thing is the integration function here. What will be the value? So if I have to divide this, in the end of the day, I have to divide Q with this P of T, right? I have to divide that with P of T. So what is the value of P of T? Anyone knows? What will be the value of P of T? Not a Gaussian function. It has to be a scalar value. What will be the scalar value that we have here? Exactly 1. Why is that? Why is 1? Exactly, because Gaussian is a probability function, right? Gaussian here, Q, the multiplication of your top side is a probability function. Gaussian is a probability function. And if you integrate probability function in this case G, so if I have to write down the proper thing is that P of T equal to now Gaussian of W and N as N T W, right? So what is the integration of that? 1, because it's Gaussian function always is a probability function, and the integral of the probability function is 1. Remember the property of a probability function in the very beginning. There are 2 properties. The value of the probability function has to be between 0 and 1, and the integral function of the probability function has to be 1.
Yeah, but you're integrating across W.
Yeah, so this one is probability of W, right? This one is P of W, right? P of, in this case, not the integral of P of T, but integral of P of T W with respect to W. This one is P of T. P of T equal to integral of P joint property with W, TW. And this one, this part here, is a Gaussian. Any questions here?
So basically proving that both the likelihood and prior is Gaussian, you just approximating that the study of likelihood times prior.
The prior time likelihood will have the multiplication of the 2 will be Q, and Q has to be Gaussian.
But remember at the beginning when we were doing the math, we just assumed that the likelihood times the prior is equal to the math, right? The maximum study. We were ignoring the evidence at the beginning.
Yeah, because we don't really get the property of the posterior.
Remember, we're saying that the posterior is approximated to the likelihood times the prior.
It's not approximate. That one is in proportion. Yeah.
But now, right now, you're just dividing by one, so it's not squared.
Well, we do not know whether this one multiplication of this is like NAP. It's not NAP.
I'm not saying it, just taking out the elements. Assuming it's one.
Yeah. That will be the same. Yes. So you will see later on that if you use NAP and you use full Bayesian, the answer will be the same. But in NAP, you don't have the opportunity to get the answer. But here, except from the answer, in this case W, you also have the values to obtain the probability of your W. Yes. Good questions. Any other questions? Okay, so if there's no question, that's the thing that we have to do, right? Now the question is that how we can have this Q. That's the question, how we can have the Q. So that's the question that we want to solve. Q of W equals to P of W, sorry, P of P bar, even W bar, P of W bar. And we hope that this one will give you Gaussian. We have to, later on, we have to force it to be Gaussian function. And this one, we know that this is a sum over n, sigma n Tn, 1 minus sigma n, 1 minus Tn. And this one is a Gaussian of W and 0 as 0. Okay, so now how we can force it? I will not explain again. We actually already learned about this last week. The basic idea to make this Gaussian, to force it to be Gaussian, is through a technique called what is the technique? Laplace approximation. Okay, so the technique to force this equation to be Gaussian is called Laplace approximation. And in Laplace approximation, there are two steps. Step 1 and step 2. Step 1 is to find, basically, if this is your true signal, your multiplication between the likelihood and the prior, right? Then the basic idea is to find the mode of this function, the blue function, find the mode of the blue function, this one. And that one is called x0, for example, or in this case, you can call it xMAP, because we know later on that this is the xMAP. Oh, by the way, let's put the exit in the proper way. So the exit here again is W, right? And this one is P of W. P of W given P. Okay, so that's the posterior. And this one is called WMAP. And WMAP is actually the mode of the blue function, the blue curve. All right. And the mode of the blue curve is actually equal to the mean of the red Gaussian curve. So basically, that's something that we want to find out. WMAP. Why this is MAP, I will explain later on. But basically, this is W star that we want to estimate. Any questions so far here for step 1?
The blue curve is the result of multiplying the likelihood and the prior.
Exactly. Yes. Any other questions? Again, the blue curve is the multiplication of Gauss of the prior and the likelihood. The second step, basically the first step, the first step here, the goal is to find the mean of the Gaussian curve. Yes.
What will happen if we have two modes?
It's impossible if it's two more. Well, it's possible, but in that case, you have to imagine that this one is somehow the two hills exactly the same. In that case, there's no choice. You have to choose one of them. Because actually, if you have two hills, something like this, it's impossible to be approximated with Gaussian. Right? Your Gaussian, sorry, your Gaussian is not possible to be a good approximation, basically, right? Unless, that's a good question, unless they are very close, like this one, for example. If you have something like that, right? That one will, but this one, the mode, for example, you just choose one of them. The mode, you choose that one, for example. If you do the approximation, it's not bad anyway, right? Because these two are, unless they are very far apart, if very far apart, it means that the approximation of Gaussian is not good in the first place.
Modes far apart,
Yeah, so that's another good question. Basically, it's come down to the accuracy. How good is your error function of W? If the error function of EW, we have an error function, objective function, right, for E of W. If it is too big, for example, too big means of course it's also relative, but compare to your other data set, for example, and your data set that you think is acceptable is in the round of 0 to 5, for example, then you use that as an indicator. Okay, any other questions? Any other questions, anyone? Okay, so that's step one. Step two is to find the covariance. And we learned last week, we can use Taylor series to do some analysis. So we use the Taylor series to do some analysis. And basically, we can find A, which is A is so we can write down the equation with using Taylor series analysis to make this W. So I will be consistent here with the parameter used. So assume that W is a single scalar value, 1 by 1, for example, for the sake of clarity, for the sake of easier discussion. So FW is f of x0 exponential function of minus a divided by 2 x or W minus W0 or WMAP, W0 or WMAP. So here W0 equals to WMAP. So that's the idea. Okay. So in this case, we know that the standard deviation, in this case, sigma square equals to 1 over A. So that's the standard deviation or covariance. Assuming that W is only one dimension, only a single W. Any question, anyone? Okay, so I will not explain this again because I already explained how we can use the Taylor expansion last week. So please look at the recording if you are not sure how to do this to get this function. Okay, so basically, as I mentioned again, that this one we can use MAP to get WMAP. And WMAP is the mean of the Gaussian. Any questions here for the mean of Gaussian. Okay, so now for the covariance, we use because W is not a single variable, W is multiple variables, W1, W2, W3, depending on the value of M. So for this one, for W vector, our equation becomes, let me see. Our equation becomes f of W bar equals to, it's basically the same as this one, but I expand it to a vector. Instead of scalar, I use a vector for the function that I have. A divided by 2 pi power to half exponential function. Let me see. That's the wrong equation. So this one is the determinant of A power to half divided by 2 pi T divided by 2 exponential function of 1 over 2 W minus WNAP or W0 transpose A W minus W0. Right. So that's the definition of covariance in using Laplace approximation using parallel series. Any questions so far here? That one, the last equation for multivariate function when you have W as a vector. So anyway, this is how the Laplace approximation has to be done. So in our case, WNAP is already clear. We can get this one from MAP function, right? Or MAP technique. Now the question is that how we can get A in the application that we have, how we can get A. So A actually is a definition that we also learned last week, where A is A minus second derivative of, let me see, of log FW. So that's the definition of A. When we discussed about A there, that's actually the definition of A that we discussed last week. So last week, actually A, if it is a scalar function, A was minus G squared T W squared log F of W. So this is the definition of A we obtained last week. So that one is only to make this to become scalar, to become vector. W from scalar value, this one is scalar value to become vector. But that's the same thing, they're only the second derivative. Yes.
Since A is the second derivative of log F of X,
Mhm.
W.
Mhm.
And F of W contains A inside it.
No, this is this one. Let me think. We already done this actually last week. So this one is when W equals to when W is, let me think, what's W? So yeah, W equals to W and or W0. So we have W0, and we insert that W0 into this function. So further, you do the second derivative of this FW. FW is a function. You already know the function. FW is this blue function here. So this one is FW. You know the function of FW. You have a second derivative, and then you replace any remaining W with W0, because W0 is this one there, right? And then you can have some value there. And that value is equal to A, negative A. Is that clear? Can I repeat what is the meaning of this one here? That one means that you have FW. FW is this line here, this blue line here, that is FW. It's a function, it's an analog function. And you have to do the derivative twice. That's called second derivative. And the second derivative will give you this function here. That's the second derivative, right? And in the second derivative will contain W, contain some unknown variable. But you replace that W with W0 or W and AP. And then you will have some value there, right? Because you replace the variable scalar value. Then that one equals to minus A. Yes. FW, this one is the approximation. This one is the Gaussian approximation. So this one here, let me see, the green box here is the approximation of W. So in this case, I change it to red so that it can be clear. This red is actually this one, the Gaussian. So the right hand side is the Gaussian. The FW here is this one, the blue one. All right? Is that understandable? Sorry, do you have any questions then? Which one that you don't understand? Which one do you understand? Because if you don't understand, then I do not know which one is that you don't understand.
You are using the same list of F for two different functions. So we are thinking that you are referring to the same function, but in reality you are referring to two different functions.
They are not the same function. So this part is Q, right? QW. So this part here is QW. And A, so I will remove this one again. The definition of A, because we do not know A there, right? So you have to have the definition of A equals to, by the discussion that we have last week, is P squared PW, W squared, F of W when W equals to W0 minus. So this one, this variable here, is the second derivative of your blue line. Is that clear? Okay, so I understand. So when you say that it's the same function, I understand. So this one, forget about that one, and so this one is QW. So this better now? This is QW, right? So that's QW, and we want to have A from F. F is the second derivative of the blue line. Well, the F that one is the second derivative of the blue line. Okay, anyway, so any questions here?
So omega 0 is
Omega 0, W0. W0 is WMAP, yes. W0 is WMAP. Yeah. If you confuse, it's fine. I mean, today is the last lecture, so I have to be a bit faster. So that's why some of you have been confused because I explained, in a faster mode. But if you don't understand this, oh yeah, that's lock. Sorry, that's lock here. That's the lock here. So this is a lock here. Yeah. So your question is what? So UW is this one. UW has to be Gaussian. So remember in the first place here, this one has to be Gaussian. U has to be Gaussian. And that one is the red curve that we want to find. Okay. And to find the covariance or standard deviation of this Gaussian, you have to use log F, the derivative, the second derivative of log F. Yes. This one, you can assume this one is QW. Yeah. Again, QW and FW are the same thing. I mean, well, not the same thing, but you want to approximate F with Q anyway, right? In the end of the day, you want to approximate F with Q, and that's assumed to be the same. Any other questions? Okay, so again, this is normal that you don't understand because this is the last lecture where I have to cover up all the possible material. Okay, anyway, so that's the way that we have A. So in practice, let me see. So F here, remember F here. F here represents so this one actually represents the E of W. Log W is E of W. So what is E of W? Right. So I will look. Let's look at the previous discussion for classification. So let's look at the MLE, right? So this one is the MLE classification. In this MLE classification, we only use for likelihood. So this one is only likelihood here. So this one is only likelihood, right? This one is only likelihood. So at that time, we learned about error function. After we have data modeling, we have error function. And in error function, we define as the error function of log P. This is only this one, the P here is only for likelihood. But we define log P as EW. Agree with this? If you confuse this, I mean, in likelihood estimation for classification, we define E as log P. If we only consider likelihood. But now in our case, we have to consider also not only likelihood, but also prior. Agree with me here? So your L function consists of these two terms, but they are under logarithmic operation. So the definition of E is log prior multiplied by likelihood for N and P. Is it clear here? And this one, P of this, is something that we want to approximate with Gaussian. This one we want to approximate it with Gaussian, correct? Right. And this one, previously the multiplication of P and P of W, we use SW. Okay? The multiplication, the real multiplication is SW, which is the blue line, the blue curve. The approximation is QW, which is the curve of Gaussian, the red one. Okay? Now, E is a log minus log of FW. Agree with this? So remember that E of W is log minus log of FW, where FW is the multiplication of your likelihood and prior. Any questions here? Anyone don't understand this? Okay, so keep that in mind because we use this one, log F. Now I change this into E. It's the same thing, right? Well, not the same thing. The minus is gone. Okay. Because EW is minus log FW. So now what is this one? Is the second derivative, right? So this one is basically the same of saying P of PW, P of PW of E of W. This is the same thing, right? Agree with this? Agree with this expression? The first in the parenthesis here is called first derivative. And then if you do another derivative, the whole thing becomes second derivative. And actually, you also learn this one, the first derivative. So look at the minimization now. This one, P of PW, P of W here, right? That one is the first derivative. When you try to do the optimization, the first derivative equal to 0, basically that's the first derivative of E. Right? And we know that this one is the first derivative, the gradient. And this gradient is, well, again, it's this function here. This one without equal to 0 is the first derivative. And if you want to have the second derivative of this, if you do the second derivative on this, what we will get? This is the first derivative. My question is, if you have the second derivative, which is T over TW, TE T over TW, then you have to do the derivative for that function, right? So now my question is that, what is the dimensionality of the derivative? What is the dimensionality of the first derivative? What is the dimensionality of that? N by 1, right? So now you have N by 1, and now you have a form like this, T of W, and there is another function called G, for example, J, for example, right? And J here is N by 1. J is N by 1, right? Now, what is the dimensionality of the whole thing here? What is the dimension of the whole thing here then? N by N. N by. It's become a matrix. The second derivative of a vector with respect to vector will give you a matrix. In this case, N by N. And we learned that actually this one, the second derivative, we know that the second derivative is called H, which is called a Hessian matrix.
Is it H or H member?
That one is a good question, but I think it's H. Yeah, I think you should look at the textbook, but I think it's H. And this one is n by n. This one. Okay. So basically, we can have this second derivative, and that second derivative is still the same as the Hessian matrix. And this one, A, is the same as H. Is the same as H. So the Hessian matrix is your covariance. The second derivative of your error function is your covariance. All right. Any questions here? And if you look at the textbook, or maybe if you look at the MLE lecture note on MLE, actually I define H equals to S0 inverse plus phi transpose R phi. You can have the definition of this on the lecture note. So actually H is known. If you know the error function, you know this H. You can obtain this value of H. It's a matrix. Again, it's a matrix n by n. Okay. So anyway, so in conclusion, after we have A, we have H. In conclusion, we can have Q now, Q of W bar, which is a Gaussian of W with mean of W and AP, and or you can put it in WN and SN, where WN equals to WNAP. So you can use NAP to get this estimation of W, and the covariance of Xn here equal to H. Again, I'm not sure this H inverse, so let's put in the proper writing. So this one is S inverse. If that S inverse, that's Sn. If Sn inverse, it is Sn inverse, I mean, so Sn is equal to H. In other words, if you expand it, then your approximate Gaussian is H, the determinant of H, power to half 2 pi power t to 2 exponential function of 1 over 2 W bar minus W and EP bar transpose H inverse W bar W and EP bar. So that's the Gaussian approximation for your posterior, the multiplication of likelihood and posterior and prior. Okay. So in this case, as we go back to the original goal of this training process, is that we want to have the posterior, series posterior, and we can have PT of W, P of W divided by P of T bar, and this one is usually QW. And QW here is that one. Okay. Any questions here? So basically, your estimation of W is this one. This one is your estimation of W, the red one. The green one is what? The green one is, yeah, covariance is what? Intuitively, uncertainty. So W and AP, you can get the prediction of your W, and there is uncertainty in this prediction, and that's represented by Sn.
So both classification and regression reach the same thing.
They are the same thing. So that's why people say that retention and classification are the same thing. Yeah, you can see that mathematically here they are the same thing. Yeah.
This is it's equal to SS0 plus phi transpose of.
Yeah.
What's this?
This one, right? Yeah. I have to go back in the MLE. Let me click that one. Let me see what I have MLE. Lecture 5. I already shared lecture 5, right? You can have lecture 5 actually already. So MLE, this one. R is this one. It's basically sigmoid function. It's a diagonal matrix.
The phi is the delta.
Phi
The phi.
Phi.
Phi is
Phi is the, phi is like phi, right? This one, remember what is this? Yeah, what is the dimensionality of this? N, are you sure?
n by n.
N by n, because n has to be larger than n. So this one has to be larger than the second one. Okay. Any other questions? And this one is actually the last assignment, right? The last part of the assignment. CA1 part 4 is implementing this.
Is the assignment asking for the predictive distribution?
Asking for?
Predictive distribution.
Yes. Next one is predictive distribution. Yeah. Because I have to be quick in explaining this because we are running against time. Any other questions? Any other question, anyone? Before we move to predictive distributions. But importantly, of course, your understanding. You need to understand the whole thing here. So if you have any questions, please let me know. Okay, so let's move on. There is no question. Now, the next question is that we want to use predictive distribution for classification. Predictive distribution. I have to warn you that the mathematics become more and more advanced. So it will be more and more difficult to understand. Okay, so the goal here for predictive distribution for classification is to obtain what kind of expression that we want to have in predictive distribution. P of P mu given P bar. Yes. So given the past data, we want to know what, given the past in terms of the regression prices, we want to know the future price, the probability of the future price. Now, in classification, what does it mean by this? In classification, if you have a space, imagine that you have space of x1 and x2, right? Two-dimensional space for simplicity, and you have positive here and negative here, for example. So what it means by PT nu T bar? Where is PT nu? Where is PT nu? By the way, PT nu here is testing already. This one is already testing. So testing and training are merged now. Okay, so it's different from the full Bayesian. In full Bayesian, in this full Bayesian, the training is done separately from the testing. Because in the training, we only estimate W. And then we use this W so I can tell you here, if it is Bayesian, full Bayesian, in full Bayesian, we have positive, we have negative, and your W is this one. That circle is your W, the estimated W, WMEP. That's the W. And once you have that, you use this one to decide, given a new data, so assume that new data is a point here, then you know that this new data is outside the circle. And that's why it has to be negative. That blue data is test data. So if it is the test data, the blue point is inside the circle, you know that it will be positive. So there are two separate processes in full Bayesian: the testing and the training and the testing. But the expression in predictive distribution is very different. Of course, we still have training and testing, but the expression itself doesn't separate the training and the testing. Okay, so basically, in predictive distributions, we want to know TU, and TU can be anything. TU can be here, TU can be here, TU can be there, can be everywhere here in the space. So what does it mean by PTU given T? How can you imagine that? So your imagination should be based on the color. I cannot write this color because there is no gradation here. Oh, there is. So imagine that if it is very dark red, right? Very dark red, it will be in the middle. Very dark red. That means that the probability of being red is very high. The probability of being red there is very high. That would be in the middle. But then in the boundary, in the periphery of these distributions, it's getting lighter and lighter. So it's getting lighter and lighter. Something like that. You can imagine that the probability in the middle, because the middle is the center of the cluster of the red, of the positive, the probability in that area is very high. But in the periphery, in the edges of the cluster, it will be less certain. Is it imaginable? And that color, the intensity of the color represents the probability value that you have there. So for the green is the same. The green, so at the offset here, it will be very, very intense. Very, very intense, I mean, the green one. So let me see. So the green here is very intense there. But once it's in the periphery, nearby the red, nearby the plus, the positive, it becomes less bright, less intense. Means that the probability is lower. And that's what this makes it more interesting. Because in this space, in this factoring space, we know the probability of any possible point. Does it make sense? And you cannot have this using full Bayesian. Because full Bayesian only gives you this red line. Only gives you the red line. And if it is positive or it is blue point in the negative side, outside the blue, outside the red, I mean, outside the red circle, you do not know whether this is what is the probability of that. You only know that it's positive and negative. But you do not know what the probability of that being negative. But in the predictive distributions, you know the probability. You know the intensity of the color of that location. Right? So for that reason, predictive distribution is much more powerful than full Bayesian. Is it understandable? Okay, so if that's not understandable, I can give you, actually, I already share with you the instruction is already there, the instruction for predictive distributions. Yes.
The full margin to plot the predictive distribution, right?
Yeah.
So it's the same.
So this one, right? You see that the color here. So the red, actually the red is going to the blue area. So it's a bit confusing in terms of the color, but if I put blue on top of the blue, you will not be able to see the drop. So I deliberately swap the color. But anyway, the red, deep red there means that the blue is very confident. But the yellow one means that it's less confident that it belongs to the blue point. If it belongs to the red point, it will be very, very dark blue. But if it is at the boundary there, it becomes green, means that the certainty, the probability of belonging to red or belonging to blue is very low. So using predictive distribution, we can have this probability value in the testing domain, in the testing space. Right? Does it make sense? Any questions here?
No question.
Yeah.
But maybe it's maybe on the previous lecture. So I think for the classification, it's clear how predictive distribution is doing. How about the regression?
Yes. For regression, it's the same thing, but it's a bit more difficult to imagine. In the predictive distribution for regression, oh, sorry. Okay, so this one here, this is a regression. In regression, we have H nu, this is the price. And this one is price actually T, right? Sorry, the distribution is about T. So this is T nu. And the x-axis here is actually price. The y-axis is the probability of T nu given T bar. Okay? And assume that this is T nu from NAP. And you have a probability function there. In the extreme case, let's assume that this is very, very confident. Okay, so let's forget that. So any value is fine. So this is your predicted distribution, P of T nu given T bar. Right? Now, of course, if it is here, you can see what is the probability there. For example, 0.7. All right. Now, you know that it's very likely that your house has that price. For example, 100K. Your house will have a price of 100K. And that's the best estimation for that time for X nu. But you can also play some, play some imagination. For example, what would be the probability if I want to increase it? If I want to increase it, because I want to increase my profit, right? If I want to increase my profit, and what will be the probability of this new path? And I can also know that one. Not only that I know the price, the best price, but I can also know what is the probability if I increase that in certain margin. And that's also important, right? In your decision making. That's the meaning of predictive distribution in regression. Yes. Go ahead. Sorry, are you asking about noise distribution? It is related to the noise, of course, because it is based on noise. But noise doesn't give you the probability of T given P new. Doesn't give you this mathematical description. You can somehow implicitly interpret noise. So, when you say that, you have price, and then you have X, and then you have somehow like that, and then this Gaussian noise is what you want, what you meant, right? But that one doesn't change with this price, doesn't change with the P new, doesn't, you know what I mean? It is only in the training process, gauging your, but of course you can somehow infer, but it's not exact probability that you want. Yeah, will be different, totally different. Not totally, but proportional. Any other questions? Okay, so this one is our goal, to have this probability space. And actually, this one is the last part of your assignment. Okay, so that's our goal. Now, how can we get this, right? How can we get P of P new given P bar? Okay, so as usual, we need to do something here as a first step. What will be the first step in predictive distribution? How we can expand it? No, I mean, if you want to expand this and probability expression, right? How we can express this further? Yeah, that is called Bayesian, right? If you use Bayesian, you can expand it. But in predictive distribution, you can't use Bayesian to expand. What else? To expand. In predictive distribution, we always want to marginalize. So remember this one. In predictive distribution, we don't use Bayesian rule or Bayes rule, but we use marginalization. And if we do marginalization, what kind of mathematical expression that I have to write? Integral, right? Integral. Integral of P new and combined with joint probability with W bar, right? So I will explain later why is W bar and T bar is W bar. This is the joint probability of W and T, right? If you don't understand this, it's actually P. Imagine that if you have P T new is integral of P T new W P W. Or if you still confused, PA equals to integral of PA given with P TP. Okay? Any questions here? Okay, so if you don't have question on that, that's the called marginalization. And why W? Why do you use W here? And why don't you use X, for example? Yeah, why we want to get rid of W? If we want to get rid of W, but we see that W is beneficial as well. Yeah. So why W is beneficial? Well, W is really the parameters of the circle that I defined here. In the end, you have circle, right? And that circle is useful. Although it doesn't give you the probability, but it's useful. Useful, but we don't want them. This one is useful, but in the end, as you look at this one, we don't use that circle anymore. Is that imaginable? The logic? Yeah. So that's why we marginalize, because we don't want to have circle in our end goal. Anyway, so this one, if we do the expansion further, P of P new given W bar T bar P of W bar given T bar T of W. This is product rule, right? Okay. Right. So this can be removed. T bar can be removed. Why is that? Why can we remove T bar? Yeah. If you know W, you can decide already, actually. So even W, you can decide whether it's positive or negative. So you don't need to have all the samples, the positive and negative, you don't need anymore. So that's why we say that T U is independent from T bar given W. So then the equation becomes P of T nu given W, P of W bar T bar T W. Right, so as you can see, there are two equations here, or two terms. So for the first term, P of T nu given W bar is, well, this one is what kind of expression is this? It looks like our likelihood, right? Our likelihood is defined in this way. And we know that our likelihood is become sigmoid of W transpose phi x star or x nu. That's our definition of likelihood, which is the sigmoid function. Normally, I just put it sigmoid, but this is the sigmoid function of Yn, and in this case, Yn is W transpose phi. Any question, anyone? Okay, so there is the likelihood. Sometimes I express this in like this, W transpose phi nu for simplicity. Okay. So let's look at number 2. So let's look at number 2 now. So number 2 is P of W given T bar. Yeah, we need to expand this because we don't have this term. This term is what does system look like? Look like? Not higher. Previously we have this actually is posterior. Right. This one is look like our previous posterior, and posterior was defined as P of T bar W bar P of W bar divided by T bar in our previous discussion, right? And we know that it can be approximated using Gaussian Q bar, where Q bar is a Gaussian function. W and AP and S and D. Any questions here, anyone? Okay, now we have to solve this. Look, this one, what function is this? Number 2? Gaussian. It's Gaussian. How about number 1? Is a sigmoid. This becomes a problem because the sigmoid multiplied by Gaussian, sigmoid is something like this, multiplied by Gaussian is not really look like Gaussian. Doesn't really look Gaussian at all, right? If you multiply this one, it becomes something like that. It's more look like sigmoid than look like Gaussian when you multiply these two. So we have a problem here. The multiplication doesn't look like a Gaussian. If you force this to be approximated like Gaussian, the approximation is a bad approximation. So we cannot use Laplace approximation in this case. So we have to do something else. So what is the something else here? The integration here is a problem now. So the integration here is the main problem. It's not, doesn't look like a Gaussian. Now the solution is another special case. The solution here is a special solution. I think this one is a special case. And this for this special case, we rely on a sigmoid function. There is a special case about sigmoid function, which is called probit function. This is a special case for sigmoid function, which is called profit function. So what is profit function? Profit function is defined as phi. Please don't get confused with basic function phi. This is totally different function. It's normally called phi, so I just follow the notation phi here, which is called profit function, or for example, x. You have a variable, and the profit function of this variable x is integral from minus infinity up to x Gaussian of theta with mean of 0, 1, p theta. This is called profit function. So how does profit function look like? Well, it look like something like this. The mean is 0. The standard deviation is 1. That is G. This one is G. The blue one is G. G is theta 0, 1. Okay. Any questions so far? Now, assume that you have x. Your x, let's say that your x equal to 0. Let's assume your x equal to 0. So this was x here, assume equal to 0. What happened then? What is the meaning of that expression? Integral from minus infinity to 0. What does it mean by that? It will be this will be the area under the curve here until that one. That's the area. The area means accumulation. The accumulation of this blue line. And if x is defined somewhere here, for example, if you define x is somewhere here, I do not know, x is a positive function. And if you, let me see, and if you have another graph, and this graph is x, and this one is phi of x, how does phi of x look like? It looks like sigmoid. That's right. It looks like sigmoid. Depending on the parameters, depending on your one here, it will look like sigmoid. If it is a certain case, it will look like very much look like sigmoid. So profit in sigmoid function can be approximated by profit function. So that's the key. The sigmoid function can be approximated by profit function. Sigmoid can be approximated by profit function. So this is one thing that we have to keep in mind. Now the question is, what is the speciality of, what is the unique property of profit? Why do we care about profit? Why profit is used here, right? So the second point is that there is something interesting about profit because the integral function of profit lambda x multiplied by Gaussian x mu sigma square dx equals to profit function itself, which is mu of sigma square plus minus phi square power to 1 over 2. So this is why profit function is useful, because the integral of profit function multiplied by Gaussian can give you a profit function. Means that it can solve the integration function or the integration problem. The integration problem now can be solved based on the second equation. But the second equation relies on the first assumption that the sigmoid can be approximated by profit function. Yeah.
The second integral of Gaussian function multiplied by an integral of Gaussian function will give you a profit function, because the profit here is an integral of
Yeah,
Gaussian.
so this is double integral. Actually,
Yeah.
if you look at that point. But you have to be careful there. This one is a special case. This one is a special case when you have this function. It's not just Gaussian.
Is 0 and standard deviation 1.
Yes, that one will somehow, well, this one, there is a one here will decide what kind of function that you will have here. There's a lot of variation if you change one there, right? And only one of them that can approximate sigmoid. Okay, but so in other words, sigmoid is a special case of probit, and regardless whether it's sigmoid or not, probit can be used in this way. When you multiply probit with Gaussian, it can give you probit. And because sigmoid is a special function of probit, then sigmoid can also be approximated in this way. Means that we can use probit approximation to solve the integral problem, the integration problem. Yeah. Any other questions? Yes.
So I see that when you have x equal to 0, it looks like sigmoid from minus infinity to x equals 0, right? Like this.
Yeah.
But when you have x, I think you need to lower your standard deviation, right? To have
So this one, the second graph with the x-axis is x. So if this x is actually not is 0, for example, let me give you one dot. If x equals to -1, it gives you another dot. If it is equal to 1, then it gives you another dot. So when you draw a graph based on the change of x, then you will have sigmoid look like function. So the second graph here is called accumulative distribution, but it's just a name, not really important. Anyway, any other questions? Right. Okay, so now we can solve the integration problem using probit. The question is how? How we can use this probit to solve our problem? The main difference that we can see here within these two equations. Let me write the problem that we have. So the actual problem that we have, the actual problem, actual equation, actual problem is that we want to have P of P nu given P bar equals to the integral of sigmoid W transpose phi nu multiplied by Gaussian W WNEB as N as capital N DW bar. So that's the actual problem that we want to solve. So you compare the green equation and the red equation. So what is the difference there? Yeah, so this one, first of all, when you look at this part here, what is the dimensionality of this part? What is the dimensionality of this? 1 by 1. Okay. And if you look here, what is the dimensionality of this? Is also 1 by 1. So we find that part is exactly the same. But this one now is 1 by 1. But here it's not 1 by 1. So we have a problem there. It doesn't really match. Okay. Look like they match, but they are not really exactly matched. Because this one is a multivariables Gaussian, where this one is uniform univariate Gaussian. So there is still something that we need to work out. How we can change this one into something like that. So then we can use directly that equation. Okay, so let's bring this. How we can change this, right? So let's copy both of them. Okay, so that's the goal. The goal is this one. The goal is that one. Right. First of all, we can create a new variable representing this. So we can have A new is a scalar 1 by 1, which is defined as W transpose by mu. Well, A new is similar to Y new, but I just use A new here. Again, this one is 1 by 1. Now, with this expression, I can have P T new of T bar phi A new Gaussian of W bar WNEP bar Sn W bar. We know that we have a problem with this, so we have to do something with the second term. So the second term, the basic idea is that, let me think. Let me say the goal first. The goal is that we want to transform this one into something like G A nu A W N E P W A N E P and A N E P and a standard deviation and N. This is something that we want, right? So everything is a single variable, 1 by 1, 1 by 1, and 1 by 1. Now the question is how we can do this transformation. Okay. So from W new, what kind of transformation is that? If you look at the definition here, what kind of transformation that we have? It's called linear transformation, because I can have B here and B equal to 0. I can have B there and B here equal to 0. And this equation here is called linear transformation. So we transform a single multivariate Gaussian into a single variate Gaussian or univariate Gaussian, and the transformation is a linear transformation. So if it is linear transformation, assume that you have so the idea is that we have G of W bar WNEP and Sn, and we want to transform this into G A nu A NEP and sigma n. And we know that this transformation is a linear transformation. As A nu, why it is linear? Because A nu equals to W transpose, or maybe it's better to put it into more general case, A W plus B, for example. This is generic expression of linear function. I will not prove this. I will not prove it here, but you can look at Wikipedia for Gaussian function, Gaussian linear. Sorry, yeah, Gaussian linear transformation. If you search Gaussian linear transformation, you will get the proof there, the mathematical proof. But anyway, so I will not prove here. But something that I want to say here is that W or MAP, A and AP equals to A W and AP and sigma n, so this one is positive, and sigma n equals to A Sn A transpose. So again, I will not prove this one. I will not prove this one, but you can look at Wikipedia. Okay, so that's called linear transformation under for Gaussian. Now, for our case, the question is, what is A, right? So in our case, here double A and AP equals to A. A in our case is this one here. So that one is your A, capital A, matrix A equals to matrix A equals to what for our actual problem? Phi nu, that's correct. So this one is phi nu multiplied by W bar, because W bar is there, right? Plus PD. What is P in our case? P equal to 0, so we don't need to do anything. But let's look at the dimensionality here to do some proper mathematical expression. A and EP is what? What is the dimensionality of A and EP? 1 by 1. W bar n by 1. Phi bar, phi by nu, n by 1, right? Yeah, we need to have transpose. So that's why this one previously we just used this expression here to make it 1 by 1, right? So this one is transpose. So this one is 1 by n. Okay. So A and EP, if we transform the Gaussian into A form, then A map equal to W transpose phi nu. Now, that one is simple. How about sigma n? Sigma n is A. A is again phi nu, right? We know that one. Sn is Sn. A transpose is phi nu transpose. But let's check the dimensionality for the correct expression. This one is 1 by 1, correct? The standard deviation is 1 by 1, right? And Sn, what is Sn? Sn is m by n. And this one has to be 1 by n. This one is n by 1, correct? To make it 1 by 1. So this one has to be removed and moved to the first one. Okay, so this one is our expression if you want to transform the W here, to transform the expression of W into A nu. If we have A nu, the whole point here, the whole journey that we have here, this one, become P nu given P bar equals to the integral of phi A nu Gaussian of A nu A and AP and sigma and D A now D A not just D A nu. So this one our new equation.
Same relation of phi in the problem function, right? Definite phi. The capital phi of A nu.
No, this one is still the same here, right? Small phi. Because the original one is small phi. This one is just copy and paste.
Yeah, but my question is about the original one. This
Oh, the original equation that we want, right? The original equation that we want is phi. capital Pi. So that's the equation here. So this one, the first equation, is the profit function that we want to use. The green one is the reality, the function that we have. So we want to match number 2 to number 1. So we want to have the format of number 2 to be the same format as number 1. If you look at this matching, everything match because profit and sigmoid can be approximated by profit. And this one is already Gaussian, but the problem is that this one is multivariate and this one is univariate. Right?
Integration Pi, unify this profit.
No, this one is still sigmoid. This one is still sigmoid. The original problem that we have is still sigmoid. The one in the black, this one is actually the transformation to become this. So we have to transform the green one into the red one in the bottom.
I think what he meant the sigmoid is changed to pi.
The sigmoid. Oh, sorry. I make a mistake. Sorry. Yeah. That one is. So this one is still whatever the original one. Sigmoid. Yeah. Yeah. Sorry for that. Does it make sense now?
Yes.
Okay, good. Yeah.
Well,
Yeah.
The AU is actually TU, right?
AU is not. AU is this one. AU.
Is the W transpose, which is the TU? Oh, okay. Right.
TU is we want to know what is the price. What is the so TU is the label. For example, if you have dot there, we want to know what is the TU there. What is whether this sample here in the test stage to be positive or negative. So we want to know the label.
Yeah, TU itself is the par multiplied by the W transpose multiplied by pi.
TU is TU is a label, either 0 or 1.
Because if you go to the next page, yeah, the TU, okay.
TU is either 0 or 1. So we want to know the probability whether it's new to be positive or negative. Yeah. Any other questions? Okay, so now we know we can transform the green box into the red box in the bottom, right? So we can replace that. So let's copy and paste the first format that we want to use. So this one is the reference. And this one is our new equation. Okay, so now we do the matching. So this one matches to that one. Well, it's not that match. One is profit and the other is sigmoid. How about this one? It's okay, right? Already. Because this one is 1 by 1, is 1 by 1, and everything is 1 by 1 here. It's good. The second term is good.
The sigma one is squared and the other
Sorry.
sigma itself for the standard deviation. One of them is squared.
Oh, yeah. Yeah, this one is not really nice. Put it in the other form. Sigma or something like this. It would be better, right? But you know that this is the standard deviation, just the standard deviation. Okay, any other questions here? Right. So if there's no question, everything match, that's good. So now let's solve this problem. Yeah. Yeah, it is a scalar.
Capital sigma has to be 1 by 1. It's a good great.
Capital sigma. Capital sigma. capital sigma. Oh, you mean capital sigma cannot be one by one?
Yeah.
Covariance. Okay, so what do you want? What? I don't know. I have already used many variables.
The top sigma square, the bottom sigma without square. That's
The bottom sigma without square.
so let the square go to the
So, sorry, can you say it again? I can't hear you. So, no, I use sigma n here, right?
yeah, sigma. Is it square or not square?
No, not square.
So we have to take the because the original equation in the top is square.
But I think it's the same definition.
That's the same dimension, but the top is
This one is a square.
yeah.
Yeah,
Doesn't make any difference.
doesn't make any difference. So, because this one is sigma n. I can use beta if you want. That's because square doesn't really matter, right? The matter is the variable. Anyway, so let's get back into sigma n. Okay, so yeah, you don't need to worry about the square. Any other questions? No? Okay, so now let's look at this, how we can solve this one. Basically, we want to solve the blue equation here. So the blue equation here is something that we want to solve. Okay. And we need to recall the profit. This one is profit. This one is the approximation, right? Profit approximation or profit convolution. Now here, if you do the matching, profit phi alpha x equals to sigmoid a mu. That's correct. It means that x here equals to what? A nu divided by lambda. All right. Agree with me? Okay. So in that case, P of P nu given P bar equals to the integral of sigmoid A nu multiplied by G A nu divided by alpha given A and AP divided by alpha and sigma n. Does it make sense? Yes. So I can explain to you here first. Here we use alpha x, but in our expression we only have a nu. Then in the original expression we have x. In the original expression we have x. But we also have a nu. So to be consistent with the formula, then we have to divide by alpha. Does it make sense?
Yes.
Okay, good. Any questions here, anyone? So if we divide a nu with alpha, we also have to divide the mean by alpha as well. But it doesn't affect your standard deviation because standard deviation is just move the Gaussian function basically. Any questions here? So the Gaussian shape doesn't change, only the mean that's shifted. Okay, great. So now everything is in the place. And then according to the equation here, that one, it can be, if we can approximate sigmoid function with profit, then we can also have sigmoid, which is profit, of A, because this one is mu, right? This one is mu. Mu is a MAP. divided by lambda square. What is lambda square? Lambda square is also lambda square, right? Lambda is lambda. Right? Lambda minus square, so that's minus 2. Lambda is lambda plus sigma square. Sigma square equals to sigma n, that's right. And this one is Any questions? Any questions here?
So basically, what is lambda again? You said lambda is sigma.
Yeah, we do not know yet. I will explain that lambda. Lambda is something to do. Let me think. Look here in the profit function that we have. We try to understand here. Lambda is something here, right? There is a lambda x. Although in that case, lambda equals to 1. Agree with me? In this equation, I can put color here. In this green equation, originally we don't have lambda here, it's only x. Here we only have x. If I put lambda, if I have to force myself to put lambda, I can put lambda x here. Correct? And lambda, of course, in this case equal to 1. But if I don't want lambda equal to 1, then I can bring out lambda all the time here, right? That's lambda x. Basically, it's just a parameter of x. That's correct. That should somehow affect the standard deviation as well. Well, it's not really clear here, but we have lambda x, and we just make the how can I say? Well, lambda is different from x because lambda is a static. It's a fixed number. X is not fixed number because x here it is in the graph. X is variable, but lambda is a fixed number. Okay. So yeah, so standard deviation is also fixed. What it means that by changing lambda, you change the shape of this graph here. Your sigmoid look like function will change because you change lambda. I'm not sure that the definition is lambda, perhaps, but I cannot speculate on that. What I can imagine is that, because you have lambda, means lambda is multiplied by x, and lambda is a fixed number, that will influence the shape of this graph. Perhaps, yeah, but again, I cannot speculate on that. What I can imagine or can explain here is that the shape of this sigmoid function will get affected by this lambda. Agree with me here? Any question? As I mentioned again, sigmoid function is a special case of probing. So lambda, the value of lambda, has something to do with this sigmoid case. Only a certain lambda that can give you sigmoid function. And we want to find that lambda. The lambda that can give you sigmoid function from probing. And people already try to find that. And so there is a certain lambda, which is lambda equals to lambda square equals to pi divided by 8. If lambda square equals to pi divided by 8, then it gives you profit function very, very close to only for this lambda value that can make profit function very close to sigmoid function. Does it make sense? Any questions here?
So we want to estimate. We use this biome, right?
Yes, you have to use these parameters here. You have to use this finding here. That is, lambda has to be 5 divided by 8 if you want to approximate sigmoid function before.
So we have to divide the A map or
Exactly.
the square root of pi over.
Exactly. So that one is the P of T nu given T bar, which is the equation that I am referring here, equals to sigmoid of A and EP divided by lambda square is 5 divided by 8, then 8 over 5 plus, is that 8 over 5? No, 8 over 5 plus sigma n square. Okay? Yeah.
A map itself, the top we said that
Hmm.
it will be replaced by A map divided by lambda.
So yeah, A map, what is A map? A map, if you look at the definition of A map, where is A map? This one, right? This one is A map. W transpose U. W and EP transpose phi nu. Or yeah, phi nu. Again, phi nu here is W and EP transpose phi x nu.
If we divide them by-
Not x nu. Is that x nu? Yeah, x nu. Yeah. So that one is W and AP, A and AP. And sigma n was what? Sigma n was A, this one, sigmoid nu Fn phi. Sigmoid, sorry, phi nu transpose Fn phi nu. So this is the solution basically. So in your implementation, you have to understand this. This is your implementation. So the distribution is the sigmoid function of your MAP divided by that variable. You know, sigmoid function is a property function.
Didn't we change the A and B? A map to be A map over alpha? Should we include that?
No, this one is the original function, but then it becomes this.
We go for the one above, the one that we find it.
Mhm.
So it's mu, right? So the mu for us in our case is A map, right? Divided by alpha.
No, we don't really need to go that far. This one, you agree with it?
Is that
The green one is okay, right? So the green one to this red one, do you agree?
yes.
Because the mu, it should be A map divided by alpha. This is the mu.
If you want to follow the same one there, because you're saying in the first one, it's equals to. Can you see the first equation?
Okay, so the first equation is this one, yes.
So that's it's like equals to capital phi mu, right? That's what.
Capital mu, X, yes.
In our case, the mu is A map
Uppercase is what?
sigma.
So now still number one. Still equation number one.
Yeah, but I think if you go to the Gaussian,
So let's put number one, number two, number three, number four. Yeah, number one.
the Gaussian of X mu.
Yeah, yes.
In number 3,
Mhm.
A map over lambda.
Amen over lambda. Yes.
If you go back to number 1, the final answer should be mu divided by lambda squared. So mu here is A map over lambda. So it should be A map over lambda.
No, that's not true. Because this new is that new, right?
Yes.
And-
this is our mu.
And this is a new here, and the whole thing is eight.
Yes, the whole thing is
The
dynamic.
real term here is Mu.
So replace mu with this value, which is a map over lambda.
Oh, I see. This one is the lambda. Okay. So let's put lambda then. So this one lambda is what? 8 over 5. Is that correct now? No. Square root of, sorry, I got confused. So this one, let's put it in the correct way. Let's put it in the correct. A and 18 divided by lambda, right? Is that only lambda? Lambda is square root of 5 divided by 8. Sorry? Sorry, which one I'm wrong? Which one? 1, 2, 3, 4. Which one? Which equation? 1, 2, 3, 4? 3. Equation number 3. Oh, equation number 3. Okay. Number 3. Okay. What's wrong with equation number 3? We have lambda here. So in equation 3, I have to change dx. Sorry, I cannot get that variable. So this one is the AU, right? Over lambda, yeah. And then, so what's the problem here? So lambda is a wait. Is that something wrong?
I think maybe that's why we just have the A map without the line. Because you are taking the integration.
Okay, so if this is the case, then I will have 1 over lambda here, right? Is that correct? Okay. So then, this one, we have lambda here, right? Well, this one is A map divided by lambda. Is it correct now? Agree, everyone? Okay, hopefully, yeah. But you know what I mean? This one is a detailed derivation. You can look at the textbook actually, because this one is just a detailed, not without any intuition, it's just detailed derivation. Okay, so if that's the case, what's the problem here now? Okay, so anyway, so I do not know which one is the correct one, but anyway, I just try to write down whatever I have on my notes first and see if it's correct. But this one is again, you can look at the textbook for the proper derivation. But anyway, so in the end of the day, we have 2-point function of that variable A map and sigma n. And A map can depend on W and AP, and Sn is also from Sn is where is Sn? Yeah, Sn is from the Gaussian approximation from the Hessian second derivative of your error function. So that one will be Sn, which is also from the MEP. Okay, so yeah, as I mentioned again, this is a big, long explanation, a lot of mathematics, but hopefully you can get the idea there. Any questions so far? So this is the end of the story of this distribution. Any question, anyone? Okay, so if there is no questions, that's the solution for your assignment. So your assignment ends here. Yeah. I'm not really sure. You can check on the textbook. Don't worry about the details. If you want to do it, you can do the derivation by yourself based on the textbook. Okay. Any questions? Any other questions here? Now, you want to go home early or you want to take a break? If you want to go home early, then you don't need to have a break. If you want to have a break, then you have to go home. It's very quick. That I just explained a very high level things about discriminative and cumulative classification. Very quick. It's not really mathematical. Not this kind of mathematics. Very high level mathematics. Right. So that's one thing. And maybe you have a question that I can answer because this is again last lecture for the first part of the. I think if you don't have a break, then you can finish in 15-20 minutes.
Let's go on.
Okay, good. Okay, so let's go on. Okay, now the second thing is that in classification, we have two approaches. One is called discriminative, and the other is called cumulative. So what we learned so far is called discriminative. Discriminative is what we learned so far. And the meaning of discriminative is that you have positive and you have negative, and then you discriminate. Okay, so this is the meaning. It's quite intuitive. You discriminate between two classes. And in discriminative, you cannot generate synthetic data because you cannot have any knowledge about the distribution. What I mean by that, I will explain the generative first, so then you can see the difference. In generative, for example, for the same problem, you have positive and you have negative. In generative, first, you try to find, for example, the simple case is using Gaussian, you find the mean, and then you find the parameters of that distribution. And for the second class, you find the mean, and then you find the parameters of distribution. If you know the Gaussian function of the blue cluster, then you can generate new data. Does it make sense? If you know the Gaussian function of this, if you know the Gaussian function of this distribution, you can draw sample. You can sampling from these Gaussian distributions. So if you have a Gaussian distribution in one dimension, for example, given this one, you can generate any possible sample function here. And in this case, if you sample from this Gaussian function, which will be most likely chosen? If you sampling the data 100 times, for example, this 100 data will concentrate in which value? The mean, exactly. So you can have this value here, and then sometimes you get value there. Means that if you know the distribution, you can do sampling. Sampling means generating data. Right? You can, if you know the distribution of this blue curve, you can sample new data. Although this data is not there, you can sample it because you know the distribution. And this sample data is called synthetic data. And that's why this approach is called generative. Because you can generate synthetic data. You can generate samples, basically. And that's differentiates this discriminative from generative. Because if you know the line, in this case, discriminative, for example, if you only know the line, you cannot sample the data. Of course, you know that the above the line is positive, you know that, but you do not know the distribution. You only know the rough area of the positive. Means what? In generative, you know the probability function of that, which is likely to be the area for the positive sample. So that's if you can do this kind of fitting, because it's called Gaussian fitting. Right? If you can have a fitting on your data to be Gaussian or to be a certain distribution, then you can use generative approach to do classification. What I mean by that is that if you have new data, for example, your data is in flag, for example, this is your new data, you will know what is the likelihood of this data to be positive or to be negative. And in this case, it's likely that it will be more into positive than into negative. So that's the benefit of generative. Generative can give you distribution and can give you generative new data, synthetic data. Okay.
But those data will be inside. So what's the benefit? It's going to be all those new data is going to be all positive because they are going to be inside the blue circle, right?
There's no circle or distribution function. Yeah.
You can do it. So the new data will also be following the same path.
Of course, yes.
There is no benefit. Just increasing the number of the points I have.
Well, it's useful, for example, in terms of generating data, synthetic data, why synthetic data is useful, is because in machine learning, normally you need a lot of data, right? And sometimes you only have few data here, 10 or 20, and you need, for example, 10,000. Right? So in that case, you can try to fit it first, and then generate samples. So that your algorithm can work, because otherwise it's too small. So that's the benefit of it. It's called generative model, and it's quite common approach in machine learning or deep learning.
This is the GAN.
Well, GAN is generative, exactly. So GAN, if you know GAN, generative adversarial network, is based on this concept that you try to find the distribution of your data. Okay? GAN can be used for classification as well, especially when you have a few shots, when you have a few data. Okay, so that is the basic concept of discriminative and generative, and it's very, very important concept. Because what we learned so far is actually discriminative. In the lecture note, actually I will explain how we use generative in a mathematical way. But it's very simple, you can just read there, and if you don't understand, you can learn it. All right. Now, the other question is, so far, we always assume that we have positive and negative with binary class. Means that we only have two classes. What happens if you have 3 or 4 or 5? Right? So there's another problem for multi-classes. If it is multi-class problem, what happens is that you have circle class, you have triangle class, you have cross class. Okay. So the basic idea, this multiple class is actually an open problem. Open problem means that the simple or the most common way to solve this problem is one against all. One against all means that if it is class 1, for example, then you try to have a separator that separates class 1 against other classes. Doesn't matter how many classes you have. In this case, it's just 2 basically, right? Become 2 problems. But aside from this C1 separator, you also need to have, for class 2, you need to have C2. C2 will separate C2 from the rest. But we also have C3, the cross one. Then you have to have C3 that separate C3 from C1 and from C1 and C2. So basically the idea here, the most common idea is what we have one against other. And one against other has a basis in binary classification. Now, how we can use this in test stage? In test stage, basically, if you have a point here, if it is obvious like this, for example, if it's here, for example, well, it is not C1 definitely because beyond C1 is something above this red line. Above the red line is C1. It's not C2 because C2 is above the blue line. This one is C2. So in this case, this blue dot must belong to C3. But there is some ambiguity sometimes. For example, this cross here. This cross is not ambiguous. Ambiguous between red line +1 and +3, because +3 says that it will be +3 if it is below C3. And that's ambiguity for this cross blue line, blue cross. How can we solve this? Well, we solve this from the probability. The problem is or in some cases it is also distance to the line. You find the closest distance, for example. Or if you have a predictive distribution, you can look at the probability. This one is a higher probability. Okay, so that's how you solve multi-class label. Any questions, anyone? Okay, no questions? Right. Final call. Any questions? For anything that you have learned so far, any questions, anyone?
So the final exam will be after this.
After this point. Yes. Again, any questions or anything that you want to ask regarding the first part of the course? So next week is a research week, and after research week there will be another lecture, and there will be a part 2 of the course, and a bit different. That one will be non-Bayesian, means that you will learn about PCA typing, and then you learn about support factor machine, and then you learn about cross-distribution model, all these non-Bayesian, and also classification learning. So that will be part 2. Okay, okay, final call. Any questions? Yes. Sorry. Oh, in practice, as I mentioned again, I just predicted distributions. In practice, is this one. We can have this one. This space. Oh, I already explained that. That was a question there in terms of the regression, what it means by that. I already explained that. But if you want to know, you can approach me after this because I think many of them already got the answer. Okay, any other questions? Okay, so if there's no questions, thanks a lot. Good luck with your finding. Thank you. Thank you, everyone.